Hello and welcome to the final revision session for Callum Cymru for A-Level Further Maths. My name is Matthew McMillan and I'm a maths teacher at Christ College in Brecon. Today we're going to take a look at polar coordinates. So I've got a copy of the specification and the teaching guidance on the board, and we're basically going to go through each element and tick them off. So understand and use polar coordinates and be able to convert between polar and Cartesian coordinates. Let's just remind ourselves what polar and rectangular or Cartesian coordinates are. So we've got a link here. So in fact, I'm going to just turn off the polar grid and let's put this point there. That seems sensible. So, oh, that's not very good. There you go, 4, 3. So Cartesian coordinates that you learn about from year 5, year 4, maybe even earlier, look like this. What we can do though is we could apply a kind of circular grid to this situation. There we go. And we could give instructions on how to get to point P in a different way. So the way that polar coordinates work is that we want the radius, so how far to get to point P. Now I've kind of carefully chosen point P, 4 units long and 3 units up, so it's a Pythagorean triple. So that means our radius must be 5. And then the angle from where my mouse is here to get around to point P, it's not such a nice angle here, 36.87 degrees. But this is us converting from polar, Cartesian to polar. So I can move this point wherever. I think when we get around to over this side here, let's just move that in a bit. You can see that the polar coordinate, if you take a look at the angle up here, is getting to 160, 170. As I come further and further around, it then flips back to negative. So the example may present this in 2 different ways, because I guess they're saying if we start at 0 degrees over here, in fact, I'll turn the rectangular one off. If we start at 0 degrees, we could go backwards and then we're going to get negative degrees, or we could go forwards and we're going to get positive degrees. They won't really mind. Let's go back to our PowerPoint. There we go. And that's kind of what I put just down here in the box. They'll either go from 0 to 2 pi, or they'll go from minus pi to pi. The other thing to pick up is they're saying the radius is going to be greater than or equal to 0. And we'll have to think about what that means in a minute when we do a little bit of investigation of some graphs. Now, what we need to be able to do is convert from one to the other. So I basically need to take my 4 and 3, 4 units along and 3 units up, and turn it into the R and turn it into the theta. And because you're all doing further maths at A-level, you should find that relatively straightforward. R is just Pythagoras, so R squared is x squared plus y squared, and theta is just the inverse tan of the opposite over the adjacent, so y over x. We're basically very often looking to get R squared in these situations because it allows us to use x squared plus y squared. If I go back and think about how to go the other way, so from polar coordinates to Cartesian coordinates, this here is R, and because it's opposite the angle, R sine theta. So that's our y coordinate. And then this here is R cos theta, because it's adjacent to the angle, and that's the x coordinate. These things you need to learn or derive them. When I look at this though, I am basically trying to get R cos theta in many of these situations, or R sine theta, or R squared. If I end up with just sine theta or just cos theta, that might mean I can't actually turn it into a Cartesian equation. Let's have a look at doing that now. So on the left, I've written the rules that I'm going to apply. And then on the right, I've just got two kind of straightforward questions. Find a Cartesian equation for the following. Now, that first one, I mean, maybe we don't need to find a Cartesian equation for it. It's just telling us r is 5, so the radius is equal to 5. If I said to you to draw a shape where the radius was 5, you should just draw a circle with a radius of 5. If we do want to turn this into a Cartesian equation and we're unsure, we could square both sides, so we get r squared equals 5 squared. And that has then given me r squared. So I know that r squared is x squared plus y squared equals 5. And x squared plus y squared is, of course, the equation of a circle. So to do that, I squared both sides. So something to the power of 2 for both sides. The one underneath, I've got an r squared, so that's already looking good. So this is question B. That's looking good. On the right-hand side, I've got sine 2 theta. And when I look over here, that is not looking good. Firstly, I want sine theta. I do not want sine 2 theta. So you'll notice here, I've put some little hints. Let's maybe just keep the r squared to start with. And let's turn this sine 2 theta into 2 sine theta cos theta. That's a little bit better because I've got sine theta and cos theta, which is what I want. However, it's not quite there because I don't just want sine theta, I want an r in front of it. So what I'm going to do is if I think about multiplying both of the bits by r, that would give me 2r sine theta and r cos theta. If I'm timesing by r and by r again, I'm going to end up with r to the power of 4 here. Well, I guess r to the power of 4, that's r squared to the power of 2, isn't it? It's not going to look particularly nice, but it is a Cartesian equation that we've got. So this r squared to the power of 2, this is going to become x squared plus y squared all to the power of 2. And then on the left, r sine theta becomes y and r cos theta becomes x. So we've got 2x, y. And we've got rid of all the r's and all the thetas, and we're just left with x and y. So that is our Cartesian equation. Now let's take a look at an exam question involving this. So we've got a curve with this polar equation, and show by considering its Cartesian equation that the curve is a circle which passes through the origin. So I guess it's telling you to start with find the Cartesian equation. Now I'm looking at the r and I might be thinking, well, maybe if I just square both sides that would introduce an r squared. The trouble is if we square both sides, it's not introducing r cos theta and r sine theta, which is what I'm going to want. What I want to do then is I'm going to times everything, so times everything by r here. So the r will become r squared. The 2a cos theta will become 2ar cos theta. And the 2b sine theta is going to be 2br sine theta. Now this is looking much better because I've now got direct replacements for r squared, which is x squared plus y squared. 2a, I'll have to keep that. And then r cos theta, I've got a replacement for that, that's x. And r sine theta, oh, we have to keep the 2b, r sine theta is y. This is already looking very circly, x squared plus y squared. Maybe I'll just rearrange this. So I'll bring the 2ax to the left, and we'll bring the 2by to the left. And then let's complete the square on these bits. So we get x minus a all squared minus a squared. And we'll do the same with the y bit. So y minus b all squared minus b squared equals 0. And then let's make it look explicitly like a circle, because that's what they want. X minus a squared plus y minus b squared equals a squared plus b squared. Find the centre and the radius of the circle in terms of a and b. So this is a circle. I might just state that. The centre is a, b, and the radius is the square root of a squared plus b squared. Now, if we draw a little sketch of this circle, not the best sketch ever. There we go, that's the centre. We're saying that our centre is at AB, and we're saying that our radius of our circle is the square root of a squared plus b squared. So our circle must pass through the origin. Circle passes through origin. Maybe just a little sketch or something like that to show that you understand what's going on there. Because your radius is the same as the sort of applying Pythagoras to the centre there. If you're still not convinced, I do have it modelled here. So I'm just going to come out of the PowerPoint and jump into here. So here is the equation set up on Desmos. Let's make it a bit bigger. And you can see as I change the a value, the circle changes, but it is always going through the origin. And as I change the b value, you can see how the circle changes, but it's always going through the origin. If we just set both of them to play, you'll see whatever the a and the b value are, you'll always get a circle going through the origin. And that's kind of what they're saying in this question. Let's go back to here. So that's kind of done a little bit of work on converting between polar and Cartesian, and also just understanding and using polar coordinates. Let's move on to sketching curves. So we've been asked to sketch this curve. It is saying the radius is equal to some value times the sine of 3 theta. I've drawn a graph of sine of 3 theta over here because we just want to keep an eye on that. And here I've created a little table of values to help me. Now I've kind of chosen the values carefully because I've looked at my sine 3 theta graph and I've thought about the repetitions. So I can see that at 0 there is something interesting happening. At pi over 6, which is here, there is something there's another extremity, as it were, and at pi over 3, there's another point which has something interesting happening. These bits down here, that will give us an r value, potentially an r value less than 0, which we are not going to be expected to plot. And then I can see up here, when we get back round to here, we're just going to get the same thing repeating once, twice, 3 times. So when our angle is 0, the sine graph is 0, so a times 0 is 0. When our angle is pi over 6, which is this point here, the sine graph gives us 1. So A times 1 gives us A. And then when we get back to this point here, which is pi over 3, we're getting 0. So A times 0 is 0. So on our graph, we're kind of starting here where my red dot is. Oh, it's going to do something funny here. So we're starting where this red dot is, or red circle is. And as the angle increases to pi over 6, now some people might get a little bit confused with pi over 6. That's about 30 degrees, if you prefer that. So we're getting out to about 30 degrees, which is going to be, I don't know, there. And we're approaching that point. The radius is getting longer and longer and longer, and then it's approaching there. It then is going to start heading back in towards 0. And that, I guess, if pi is 180 degrees, that's about 60 degrees. It should be coming in at an angle of about 60 degrees. That's going to be roughly there. So we'll get this sort of petal coming in like that. Now, I'll try and draw the other ones. So we're going to get another petal over here. It's very hard to draw using my tablet. And we're going to get another petal down here. That point there is A. This is not particularly well drawn. You'll probably be able to draw it better on a piece of paper. But this is the situation that we have with this curve. Let's just have a look at it on GeoGebra. So I'll keep my annotations there, and it's this one that I wanted, I think. So make it as big as possible. Where my mouse is hovering, I've typed in the function. I've just put 1 times sine of 3t, and you can see over here, this is the angle. This green dot is the angle. And I can move the angle. In fact, I'll use this slide, it's a bit easier. The graph on the right then, that's actually plotting it as polar coordinates. So it's turning that angle into the radius. So as I get to here, you can see I'm at the peak of my sine curve here where my mouse is, and I've reached my maximum point over here. And then I'm starting to come back in. This is at pi over 6, I think we'd found. We get back to 0. Now this is where we get something that we do not have to plot. Can you see on here, up here where this green line is a solid line, that's giving us positive R values, positive values for our radius. Down here where the green line is dashed, that's giving us negative values. So can you see this graph is actually drawing the negative values for me? And you can see it's the sine curve is negative. So you wouldn't be expected to draw this petal that's coming out here. However, we're about to head back to a positive petal. Here you go, this is a positive petal coming out here. Now, this next negative petal, can you see how it kind of overlaps the previous positive petal? I can tell it's negative because it's into the dashed line again. And then this next positive petal actually overlaps the previous negative one. So that negative one that was being drawn, it does actually reappear as a positive petal. And then we get another negative petal here. So that is the shape that we get. Now, if I change this to an even number, so I'm going to change this to 4. You can see with a 3, we got 3 petals. In fact, if I change it to a 5, we get 5 petals. If I change this to a 4, I'm guessing we would get 4 petals, but we're getting something a little bit different. Let's just have a look at it. So the positive part of our graph is being drawn here, but then can you see how this negative graph, which we do not need to draw in our exam, it's drawing the negative graph. So this petal here is the negative graph. Now, you want to keep your eye where my mouse is here. You want to keep your eye on that and see if that gets covered again by the positive petals. So I'm going to redraw all of them, a positive one, a negative one, a positive one, a negative one, and then a positive one, and then a final negative one. But can you see we didn't get another positive one overlapping this negative one? So this kind of formation looks like there are 8 petals, but really there are only 4 positive ones that we're going to be wanting to draw. What I'll do is I've got another one which we can look at here. No, not that one. I think it might be this one. Oh no, it is that one. So I think this one, okay, I put a 5 in front of the cos function, but it's still 4x. This one kind of draws the positive petals, but it makes it very obvious that the negative petals are a dashed line. So if I draw all of the petals there, the positive ones are the ones that we want to draw, so 4 petals, and the negative ones we don't have to worry about. So the number in here is basically telling us the number of petals that we have to draw. So that's one type of graph that we might encounter. This then is another type of graph that we might encounter, and again we'll have a little explore of it, but we'll draw this one first. So it says the radius is some multiplier times 1 plus cos theta. And I've drawn the cosine graph here. So where we put a 0 in as our angle, which is here, you can see my cosine graph is giving us a 1. So this value here would be 1. 1 plus 1 would be 2, and we're timesing it by whatever this number is at the front, so it would be 2 lots of A. I'm then looking at the next kind of critical point on my cosine graph. It feels like here is another critical point, which is kind of the reason I've chosen pi over 2, because it's like a point of interest on my cosine graph. So I put pi over 2 into my cos function. I've got 0 coming out. So all we're left with is the 1 here. So it's A times 1, which is A. The next point of interest on my cosine graph looks like it's down here. That's where our angle equals pi. So I put pi into the cosine graph and I've got -1. 1 add -1 is 0, times by A is still 0. And so you can kind of see how I'm putting in this next point. That's going to give us an A coming out. And then the next point of interest is just up here, where we've got 2 pi, and then we've got a 2A coming out. So this is kind of how I'm choosing these values here. I'm thinking about where I'm getting maximums, where I'm getting minimums, where I'm getting zeros. Those will help me sketch this graph. So thinking about it, this is going to give us a complete revolution. And we're starting at 0 at 2A. So that is, I'm going to say there. Now 2A, there we go. We're then going to be heading to A, and pi over 2 will be kind of when we revolved around to this point here. So we're starting at 0 and we're going around to this point here. A is going to be probably about, I don't know, there, maybe. That might not be perfect, A. But we're going to get this kind of sort of shape getting to that point. Then it looks like by the time we get to pi revolutions, we're going to be back at 0. So we're going to be coming back in kind of like that. And then the next point is 3 pi over 2. So 3 pi over 2 is revolving around to this point here, and we're getting another A. So it feels like there's a bit of symmetry kind of here. And then we're revolving around to 2 pi. I guess that's right back to the start again, 2 pi. And we're getting this kind of thing here. I haven't drawn that particularly well. Hopefully you'll be able to draw it a little bit better on a piece of paper, but that's roughly what we get. I think we should have a look at what graph drawing software does, because they'll probably make a nicer, probably do a nicer job, won't it? So let's have a look. It's this one here. Now that looks a lot better than my one. We'll just run through it so you can see how it's drawing it. So there we go. It's starting at, because I think this doesn't have some kind of multiplier in front, and I'm making it clear that there's a 1 in front of the cosine function there. So if I increase this, we're going up and around, and then back to 0. And then we're going to go up and around and back to 2 there, which was 2A on my example. Now, you do need to be a little bit aware of what's going to happen if we change these values. So the first thing I'm going to do is I'm going to change this number here. So let's get my keyboard. 0.5 is what I'm going to put in. Can you see what's happened? We did have a dimple. Now that dimple has disappeared somewhat. I'm just going to change it to 0.6. Let's change it to 0.7, see what happens. Can you see how I changed this number? 0.8. It's getting more and more, or the dimple is becoming more and more pronounced until we get to 1, when we get it perfectly touching the origin there. So what we are comparing here is this number with the number at the front, the 1 here. If this number is smaller, then we're going to be starting to get this kind of situation with it's more like an egg shape. We'll go into the technical term in a minute. If I make this, so that was 1. If I make this bigger than 1, so 1.1, I'm making it bigger than the number at the front here. Something odd is happening in the middle there where my mouse is, and I just want to investigate that. Maybe I should make this 1.5. There we go. So can you see we're kind of getting, it's kind of a convex arrangement here. So if I follow what's happening here, we're getting all of this is positive, positive, positive. But do you remember I said that here, this dashed line here is going to start creating a negative part, and we do not draw the negative part. We're not expected to draw that bit. So this loop in here is actually a negative radius. So I guess it kind of does exist, but we're not expected to draw it. And then we're back into the positives again out here. So the bigger I make this number, the more pronounced that would be. I wonder what happens if we do it to 2. Now I'm going to put it back to a 1. So we've got a sort of situation like that. Maybe we should also think about what happens with the negative involved here. So that's going to flip our graph. So the cosine is kind of the we're looking at the left and the right. Change it back to a positive, and you might be able to guess what's going to happen if it's a sine. That's turning it into we're looking vertically up and down. So there's a positive sign. You can guess what will happen here with a negative sign. It's bringing it down the other way. Okay, so those graphs are kind of worth knowing, or at least being able to draw them if you need to. Now, let's have a look at the terms here. So the technical name is I think it's pronounced a limison. That's probably an awful pronunciation. These are the situations that I've looked at. Middle one is the cardioid, which is quite a well-known one. I guess I'm guessing it's to do with a heart. It does kind of look like a heart. This visualization I quite like. Well, it's what's actually happening is it's a circle rotating around another circle. The limison of Pascal, that's the official name. Pascal is the father of the Pascal from Pascal's triangle. And limison is, I don't think the translation is directly snail, it's something else, but I just found that interesting. So you might have to sketch some polar curves. Now, let's move on. So we've done a bit of curve sketching. And the 2 I've looked at are the 2 that are in the teaching guidance here. There are others, and it might be worth having a little think about them. Now let's have a think about tangents to curves. Find the polar coordinates of the points on this curve at which the tangents are parallel to the initial line. The initial line is that line there, isn't it? So we could have tangents here which are perpendicular to the initial line. And for those ones, we are saying, where is my x coordinate not changing with respect to the angle? The change in x with respect to the change in the angle is 0. So on this situation, I've got 3 of those. This one, though, is saying it wants tangents parallel to the initial line. So that's where we're thinking about, where is my y coordinate not changing with respect to the angle? The one at the top here and the one at the bottom here are kind of obvious, but do not forget there is a third one here. You will get to the end, and hopefully you'll get to the end of the question with 3 solutions. And if you're wondering why there's 3 solutions, that's why. I'm guessing something you could already be thinking about is maybe there's going to be a little bit of symmetry here, like whatever angle you get at this top one here, you're probably going to get the negative of the angle for the bottom one here. I would imagine also the radius at the top is going to be the same as the radius at the bottom. So if you're getting something that's not that, you probably have gone wrong. So for this one, we are taking, in fact, let's change the ink color. So we're taking the fact that dy by d theta is equal to 0. Now let's take y. Y is equal to r sine theta. And what I need to do is there is a function for r. It's given in the question. R is 1 plus cos theta. So that's what I need to put in place of r. So y is 1 plus cos theta times sine theta. I'll multiply this out. So we get sine theta plus sine theta cos theta. And then I don't want to use the product rule to differentiate. I would rather combine the sine theta and the cosine theta to get half sine 2 theta. And that's why I've put the trig identities up here, because you're going to use these a fair amount in these types of questions. So if we differentiate y with respect to theta now, then we're getting cos theta plus 2, sorry, not 2, scrap that, cos 2 theta, because the 2 cancels out the half. For a horizontal tangent, I would like this cos theta plus cos 2 theta. I want that to equal 0. Now, it's not very nice if I've got a theta and a 2 theta, so I'm going to use one of my trig identities here. Again, it's this one here. So cos theta, and using that double angle identity, it is 2 cos squared theta minus 1 equals 0. So we get 2 cos theta minus 1 or times cos theta plus 1 equals 0. So cos theta equals a half, or cos theta equals 1. From this one then, theta is plus or minus pi over 3. And from this one, theta is pi. And that's kind of what I was saying. We're going to get some kind of symmetry here. One positive angle, one negative angle. Haven't quite finished because, and this would be a very common mistake, find the polar coordinates. You've only found the angle so far. So when theta is pi over 3, we want to then find r. R is 1 plus the cosine of pi over 3. And that equals 3 over 2. If we do that for all of the others, I'm not going to do it because it will take a little bit of time. We then get our coordinates. This coordinate then is 3 over 2 pi over 3 because it's r theta, not theta r. And then the other ones that we get are 3 over 2 minus pi over 3. And the final one is 0 pi. If they do give you a sketch, which they have given you a sketch here, just have a look at it and think, is that one, for instance, sensible? Yes, that is sensible because the radius will be 0 and it seems to be at pi. Are these sensible? Yes, they seem to tie up with 1 over here and 1 over here. So they look like sensible solutions. Now, we have another question here, and I'm just looking at the time as to whether I have time to go through it. I think I'll just start it off, but it might be something that you want to pause and try yourself. So the method here is the same. Find the polar coordinates of the point on C at which the tangent is perpendicular to the initial line. The only slight difference here, I guess, is this time it's dx over d theta equals 0. So we're dealing with x equals r cos theta, and r, well, we're taking that from up here, so x equals cos theta plus 2 sine theta times cos theta. I think there's a few ways you can go about solving this now. You could, well, let's multiply this out. So cos squared theta plus 2 sine theta, cos theta. So you can either apply the product rule to the sine theta cos theta bit and the chain rule to the cos squared theta bit, or you could apply some trig identities. I think that's what I did. So this bit on the left is half cos 2 theta plus half plus sine 2 theta, and then you could go ahead and differentiate from there. Once we do go ahead and differentiate, because I'm running out of time, I'm just rushing this a little bit, we do get to a situation, so I'll just kind of skip differentiating dx d theta. Eventually we get to this 2 cos 2 theta minus sine 2 theta, and because it's the tangent we want it to equal 0, we then end up with sine 2 theta equals 2 cos 2 theta, and then we divide through by cos. We get tan 2 theta equals 2. If you do go ahead and sort this out, you get r equals 1.902, and you get theta as equal to 0.5535 ... Okay, so your coordinates would be 1.90 and 0.554. So 3 significant figures. Okay, I'll leave that for you if you want to try that later. The reason why I would like to just move on is just so I can finish up by looking at the area of a sector, because then I've covered everything. So the area of a sector of a circle in radians is half r squared theta, and we're using basically the same concept. The only thing is that r is changing as we move around the circle, because I guess it's not strictly a circle, it could be a cardioid, it could be something else. So we're integrating each of the different radiuses that we get, but that's kind of where we're coming from, and that's one way of remembering it. Just remember the area of the sector of a circle. So here our area is equal to a half. Let's get the question up. In fact, so let's rewrite this a bit further down. So our area for this is a half times the integral between the two limits. And you just got to have a look at the question. It says the initial line, so that's where our angle is 0, and the line theta equals pi over 2. So it's 0 and pi over 2. Very often in part A, they actually get you to find those points because it might be the intersection of two curves. And then we're integrating cos theta plus 2 sine theta. However, we have to be careful here, because it says do r squared, so we have to square it at this point. When we do square it, half pi over 2, 0, we get cos squared theta plus 4 sine theta cos theta plus 4 sine squared theta. And we're integrating with respect to theta. When you do integrate this, though, but before we can integrate it, we need to use the double angle identities up here because we're not able to integrate cos squared and sine squared. So this is where you do need to learn these kind of off by heart. So you can do this really quickly. For this one, I'll just keep going. So the first bit is going to be giving us a half plus a half cos 2 theta. And then the next bit, because it's 4 sine theta cos theta, and I can see 2 sine theta cos theta turns into sine 2 theta, this is going to give us 2 lots of sine 2 theta. And then because it's 4 sine squared, I'm kind of having a look at this one here, and we're getting 2 minus 2 cos 2 theta. Now I'm going to skip a little bit. There is a little bit of tidying up you can do here because you can see you've got sort of common elements here. When we do integrate though, we're getting this, a half times minus cos 2 theta minus 3 over 4 sine 2 theta plus 5 over 2 theta. And the limits are pi over 2 and 0. Now, when we put those limits in, this is what we get coming out, and it's worth, usually it is actually worth showing the substitution. I'm taking a little shortcut here, but it's definitely worth showing what you get here. 4.926 dot dot dot, take away, and we're going to get -1. And it's all multiplied by a half. That gives us 2.96 to 3 significant figures. Doesn't really say the units, don't really have to put the units, but some units squared because it's an area. Okay, so I rushed that a little bit, but really I want to highlight for integrating, and you should be doing this in your normal maths course as well, when you're integrating cosine squared or sine squared, you need to be learning these double angle identities up here. And the other thing to note is just the area, just try and remember the area of a circle in radians, and it's effectively the same thing. Now, I think we've managed to cover everything that I wanted to cover. So we've had a look at understanding and using polar coordinates and converting. We've done a little bit of graph sketching and picked up that these two are the ones in the teaching guidance, most likely the ones that you might get asked about, but you could get asked about others. Thought about tangents, parallel and perpendicular to the initial line, and then thought about finding the area enclosed by a polar curve. So that's the end of this revision session. There are other sessions available, and you can go on the e-sgol website to go and have a look for them. Thank you very much.